Does philosophy make progress? It might seem obvious to you that the answer is no. Many philosophical debates going back to the Greeks remain unresolved. And when it comes to questions about how we should live our lives, this is exactly as it should be. But appearances are deceiving. Once an area of philosophy gives rise to a sustainable empirical research project, it becomes its own scientific field. This is what happened to physics in the 17th century, to biology and psychology in the 19th, and cognitive science in the 20th. When philosophy makes progress, people stop thinking of it as philosophy. Something like this has happened again recently. While philosophers have been talking about causation since at least Aristotle, only in the last few decades has a systematic framework for representing and reasoning about causal relationships been developed. The scientists studying causation are scattered across many departments, and increasingly have more in common with each other than they do with their colleagues. In other words, causality has emerged as its own field of study. Hello, and welcome to the introductory episode of Causal Foundations, a channel in which I cover the philosophical and methodological bases of causal inference in videos of approximately 10 minutes. I'm recording this after having already posted the first 4 episodes. Since each episode dives into a particular topic, I wanted to provide a preliminary episode for the sake of orientation. The main thing I want to do today is to introduce the notion of a causal model. Imagine an employer is hiring for a job, and 2 of the factors she cares about are 1, the applicant's skill level, and 2, how friendly the applicant seems to be. This scenario can be represented by the causal graph on your screen. Any factor that influences the hiring decision can be represented as a cause of that decision. To use Pearl's metaphor, effects listen to their causes. The type of model given here is a directed acyclic graph, or DAG. Here the nodes are variables. The graph is directed in the sense of containing directed edges, or arrows, and acyclic in the sense of containing no causal cycles. Causal DAGs are also called causal Bayes nets, or structural causal models, and all of these refer to the same thing. There are also generalizations of DAGs, such as models allowing for cycles, though DAGs are the most widely used. One thing that makes causal models complicated is that the variables we care about will be influenced by a ton of others it would be much easier to ignore. Perhaps one's skill set and one's interview friendliness both depend on motivation. Highly educated people might have more skills, and knowing they have a better shot at the position, also be more motivated. And perhaps the employer makes different decisions when she's caffeinated, and her perception of friendliness is partly mediated by how much the candidate smiles. Though maybe this effect differs for men and women. We see that the model can become arbitrarily complex. Fortunately, causal models tell us when it's okay to simplify the model. To start, omitting common causes is much more problematic than omitting independent causes. In fact, causal models typically make no effort to include all causes of an effect. Omitted causes may be represented using error terms, which are typically left implicit. The variables in a DAG are typically random variables, which are variables to which one assigns probabilities. So we could talk about the probability of an individual being friendly or having a particular skill level. We can also talk about the probabilities of combinations of events, and these are given by a joint probability distribution. From this distribution, one can learn conditional probabilities. For instance, we might say that conditional on someone's being motivated, skills are probabilistically independent of friendliness. This just means that once we know someone's motivation level, skill level provides no further information about friendliness. This would not be true given a different DAG in which skill causes friendliness. So facts about which variables are independent conditional on which others can help one empirically distinguish among causal models. As I'll repeatedly emphasize, facts about probabilities are not directly observed, but must be inferred from the data. You don't observe that a coin has 0.5 chance of landing heads, but use statistics to infer that the frequency of observed flips supports the hypothesis that the probability is 0.5. Probability models are thus a crucial intermediary between data and causal models. But what makes these models causal models? Causal models imply that each variable depends on its direct causes in the model, as well as on a random error term. This model implies that being hired depends on skills and friendliness, without specifying the quantitative relationship. It doesn't say, for instance, whether skill and friendliness independently contribute to hiring chances, or if perhaps friendliness only helps people with the required skills. Because DAGs place no restrictions on these functions, we say they're non-parametric. We could, of course, specify a function. This is done with structural equations. This one indicates that one's probability of being hired depends linearly on skill level and friendliness. What makes this equation structural is it indicates how the effect would respond to interventions on its causes. By convention, the effect is always written on the left-hand side as a function of its causes on the right. These equations don't come from nowhere. Under suitable conditions, they are uniquely determined by the combination of one's causal and probabilistic knowledge. This is called identification and is covered in episode 3. If you've ever taken a class in statistics, you've probably come across a model like this. Here I'm not going to walk through the details, but basically it gives the parametric and distributional assumptions that would allow you to generate data. A subtle point here is that causal models are not generative models in this sense. One cannot take a causal model by itself and use it to generate data, unless one has also identified the structural equations. The DAG's relationship to the data themselves is indirect. It places constraints on the probability distribution that is inferred from data, which combined with structural equations can generate the data. Over the course of this series, I'll be talking a lot about how causal models relate to reality. In this context, someone invariably brings up the quote, "All models are wrong, some are useful." Although I think this quote is true, ironically I don't find it very useful, since it glosses over distinct ways models can relate to reality. By way of analogy, consider the old parable of the blind man and the elephant. The one holding the tail thinks the elephant is thin and stringy. The one touching the tusk thinks it's hard and pointy, and so on. The lesson many draw from this is that reality isn't one way or another, though to me it's more plausible that each man has a partial glimpse of reality. Simple statistical models are like each man building a parameter for his observations and generalizing it to the whole elephant. This would be like trying to generate a whole elephant from a measurement of its tail. The charitable view of such models is that they're not even attempting to describe reality, but can still sometimes be amazingly useful for prediction. The causal approach, in contrast, would be for each man to acknowledge that he's studying just one part of the elephant, and to figure out which assumptions he needs to carve out his part of reality. Although this carving process will introduce idealizations, meaning falsehoods, he is attempting to describe reality, and we can evaluate the extent to which he succeeds. In this series, I'll be walking you through the basic assumptions of graphical causal models. One thing you'll notice is that most of these assumptions involve types of independence. For instance, that certain variables will be probabilistically independent given a DAG, or that causal mechanisms can be independently altered. As I'll explain, the empirical content of a DAG corresponds not to the arrows that are included, but to those that are omitted. This is surprising, since historically, the focus has not been on independence, but on dependence. Causation has been seen as some sort of metaphysical glue by which an effect depends on its causes, whereas the cement of the universe, to use J.L. Mackey's term. For me, the study of causation is not about discovering some new connective tissue of the universe, but of figuring out how it's possible to study parts of the universe without always having to deal with it in all of its complexity. In the analogy, it's about how to make the assumptions that allow us to divide up the elephant responsibly. In contrast to the large language models that are transforming our lives, causation is not about how to use as much data as possible in order to draw conclusions. Rather, it's about how to reliably draw conclusions, even when we have only partial information. Thank you for listening. For further information, check out the epilogue of Pearl's book, which remains a nice entry point into the philosophy of causal modeling, and which I've linked to in the comments.